Yeah. Let's hear it for PHP. How many people are actually currently dealing with PHP as a kind of modernization? There's one over there. What about Ruby on Rails? Ruby, JavaScript, Java, Visual Basic, I've seen. We have legacy Scala in our organization, which is too embarrassing to even talk about. I'm going to talk about like the good stuff, which is PHP. All right, let's go. There are two kinds of startups, ones that achieve some modest traction on top of a pile of code of which they are vaguely ashamed, and the ones that go out of business. And I want to talk about the second kind. I want to talk about legacy software and traction on top of legacy software and the cost of that. So I want to talk about that, and I want to do one case study, because kind of pressed for time, about a PHP app that we did to Scala. So just a little bit about me. I'm a senior engineer at Hootsuite. I've got some large number of years of Java. My background is in enterprise software modernization, COBOL and Fortran, and RPG and mumps and stuff like that, to embarrassing Java EE, which is in a way legacy to more legacy. But now it's Scala. We're going towards Scala, a powerful language, and I'm loving it, and I'm never looking back to that kind of the previous age. A little bit about us. The only important thing here is that we are 7 years old. We built our success upon PHP and that rapid development framework to the point where we've got 11 million users worldwide and 2,000 enterprise customers. So a lot of traction. So the problem with legacy software, I like to call it fossilized technical debt. Because with technical debt, you can kind of pay it back, right? You can kind of spend time on technical debt, refactoring and kind of paying it back and bringing yourself back up to zero, and then it kind of gets older and older. But fossilized technical debt or legacy code, you're spiraling out of control. Your maintenance costs are spiraling. It's expensive to host it and deploy it. It's really expensive to scale it in the modern SaaS universe. It's very difficult to test it. And when you are in a legacy environment, changes themselves incur risk, and risk becomes FUD, and FUD turns into innovation paralysis in your organization. And as a technologist, that makes me really sad, because technology should never be the bottleneck of things. I mean, the bottleneck of your organization's takeover of the world should be sales and marketing and agility, but technology should be the easy part. It should be easy to do things with technology, and that's why legacy code is a problem. And so our legacy problem revolves around PHP, a dynamically typed language. Scores and scores of lines of custom boilerplate to do things that should be done in a library, massive code base, no real modularity, SQL statements strewn throughout, no layers or anything, just the stuff that you would expect from a code base worked on by people just trying to get product out the door and fulfill a market. Very, very low test coverage. And with that comes huge risks in refactoring that code. PHP. Everyone's down about PHP. But why? Why did everyone use PHP and the Linux, Apache, MySQL, and PHP stack, the LAMP stack? Why did everyone use that 8 years ago? Why was it so easy to spin up a dynamic content serving server, a web server on the internet 8 years ago with the LAMP stack? Because of the PHP community. The PHP community made that the trivial way to do things. It made the de facto way of getting a dynamic web page onto the internet 8 years ago was PHP. Wouldn't it be great if the de facto way of getting a responsive, scalable 6.9s SaaS product into the cloud today, wouldn't it be great if that solution 6 years from now was Scala? It became Scala. Because I think with Scala, we're where PHP was 2 years into the PHP takeover. I think we have an incredible opportunity to make Scala the de facto framework to go forward. That was a little digression. So why Scala? What was my organization's reasons to go to Scala? What were our requirements to go to Scala? Well, or to address some of the legacy code. We were acquiring. There were acquisition requirements. There was our move towards providing a platform as a service and providing APIs. There was spiraling cost of serving all this stuff in AWS. We needed something scalable into the future. We needed something that would scale with our projected user base without paying half of our revenue to Amazon. We wanted composable microservices. We needed integration with our PHP monolith so that we could gradually go towards microservices. And we wanted fault tolerance and partial outages. You know when you're at home surfing Netflix and you go to your episode or whatever, and it starts at the beginning instead of starting at the 13 minutes in where you left it the last time. That's Netflix having a partial outage of their microservices architecture. The systems that store the bookmarks of your TV shows are down. They're having an outage, but you can still watch Netflix. You just have to start at the beginning and then kind of fast forward through. That was kind of the goal of what we needed. With our software as a service, we wanted, when the inevitable outages happened, we wanted them to not be 500 level errors happening to every single user. We wanted parts of the system going down when things inevitably did go down. Oh yeah, and during the migration, zero downtime. We needed to the application itself needed to maintain its enterprise SLAs, which was 6 nines of uptime, and that was a requirement straight from the beginning. So how do you modernize legacy code that is serving up thousands and thousands of requests a second to paying customers? How do you migrate that away from PHP and into, in this case, Scala? So to back up, our engineering strategy had to change to go from PHP and monoliths to Scala and SOA. So we performed iterative experiments leading to our commitments and our decisions. We always cycled around building an experiment, measuring the results and learning from that, and always doing it in production. So we did have a development environment, a staging environment, but the only thing that counted was production. Running these experiments and running these changes in production was the only thing that we focused on. And of course our decisions, of course Scala and Akka, of course we were very well aligned with the reactive manifesto. It just makes sense for a SaaS offering. We went down 2 paths. We did our own microservices architecture, which isn't in this talk, and then we modernized another monolith into the Play framework, which I'll talk about later. We scaled our team by hiring Java developers, by training PHP developers. We partnered with those rad guys at Bold Radius to do a series of training sessions, which worked really, really well. But we needed to scale our engineering practice and change our engineering practice itself. And for that, we turned to Conway's Law. Conway's Law says that Conway's Law says that the design and architecture of your system will follow the communication and team structure of your organization. So here we have the UI specialists, we have the middleware specialists, that's the monolith, and we have the DBAs handling the database. And of course, that's the monolith, the compartmentalized UI, middleware, and DBA. Instead of that, one way of reorganizing is to create cross-functional teams and aligned around vertical slices of the product that align with the microservices that you want. And so that's what we did. These are the Hootsuite product offerings right now. This is present and future, and each of these represents a engineering shift, like an orthogonal engineering shift to change the way that that we organize ourselves. So that's how we did it, kind of in an abstract organizational way. I'm going to talk about the modernization of our URL shortener, Owly. Who needs a URL shortener in 2015? Well, we do. Because one of the things that we wanted to offer was a free and automatic URL click analytics. So every URL that was posted through the Hootsuite product to the various social media networks that we supported was shortened with Owly, and we provided click analytics for free to everybody. Owly has a public web UI, so you can actually go to the system. A public API, a public web UI, so you can kind of browse to it. A public API, so that you can kind of use it as a software as a service. And then a private extended API used by our dashboard product for all URL posting. We are the provider of many vanity URL shorteners. So every time you see typesafe.es or whatever it is, I don't think it's typesafe, but you know what I mean, right? The vanity URL shorteners that are out there, a lot of those are backed by Owly itself. And up until a year and a half ago, they were backed by 6-year-old PHP code. Just some stats, 1,000 URL redirects per second, 10 images uploaded per second. Owly is the second most popular URL shortener behind Bitly that you've never heard of. T.co doesn't count because you can't go to T.co and actually it's not independent outside of Twitter. So for Owly, I kind of want to draw attention to how we found it, the legacy problem of Owly, how we scoped and estimated the modernization effort, how we executed the modernization, and a few Scala patterns, because this is a Scala conference, I need to just throw in some Scala. So each one of those little PHP icons represents an AWS instance. I think there was like 60 or something. They were M3 larges or C3 larges, so the relatively expensive ones. It was very expensive. It was a snowflake deployment. We had to call the guy that knew how to deploy it and get him to tar it up or rsync it or whatever insanity was involved with the deployment. There were no tests. It was an old version of PHP which had security holes. The business of Hootsuite's business was looking to monetize the traffic. We were getting a lot of especially on mobile and for the image landing pages. They wanted to monetize that traffic. They wanted to kind of show ads or whatever, and we were like, no, we cannot touch that code. It was total paralysis with this this valuable commodity because of legacy software. It looked like this. So what do we do? Well, on the front end, we changed the HTTP API and web UI into Play, of course. Back end, we wrote a microservice, a data microservice around the database to provide an API around persistence of shortened URLs. It was a cross-team effort, like we said before. Instead of just having platform people and everything, it was a vertical slice of this team that was enabled or mobilized to take on this modernization. Zero planned downtimes and very few bugs. I think the total downtime during this huge pivot was, I think, measured in minutes, maybe 2 or 3 minutes, measured in like 15-second increments over a couple of months. So not a lot of downtime considering the magnitude and risk of the project. And no huge scoping failures. This is what it ended up with. So Play on the front end, 9 servers and a data service on the back end, another 9 service. And this is without any optimization. We could have gone down to fewer. For elastic scaling, we could have done something different. So how exactly did we modernize it? Well, we looked at development best practices, like the modern development best practices. So unit test coverage on every single line, integration test on every API and every screen, environment parity across our virtualized environments, the centralized dev environments, the staging environment, and of course production. Proper monitoring, logging, and alerting per our best practice through the rest of the organization. And always go to production with the minimalist viable product. So every time any little vertical slice was done, push to production. And then feature flag that small slice for the monolith. So remember, we have a private API being called by the monolith many thousands of times a second for URL shortening. Well, every time there was a single slice, well, we would do an incremental deploy behind a feature flag into that slice. So we'd be using the old system and the new system at the same time in production while we were developing it. So speaking of clear scoping, scope analysis became huge. When we were staring at 500,000 lines of PHP and deciding how we were going to modernize it and how much it was going to cost, it's a hard sell, right? Because management is like, you're saying that it's an architectural change, a new system that is exactly the same, provides the exact same functionality, but it might be a little bit worse because it's relatively new code and it might contain bugs. It's a hard sell. So how do we sell the number to management? Well, we started with a user story, like the user stories you see there, and then we took a hard look at the deprecations. So API versions, screens, cross-cutting features, and deprecated technology. So we kind of thought about those two kind of orthogonal things. So user-facing stories and then deprecated concepts. The scope analysis only took a couple of weeks. The product owner and architect both signed off on the deprecations that were appropriate for them to sign off on. So the product owner only signed off on deprecations for features. The architect only signed off on deprecations for the technologies. No specifications. There were no specifications written. We just looked at the code. Anyone can read PHP. We just looked at it to find the business, to find the development scope, which is the sum. So when developing, look at the story. Then flip over to the PHP and look at the business logic. Keep in mind the cross-cutting scope alterations, both feature and technology. Clearly modularize it, but err on the side of leave it in and leave it broken. Now this is kind of important. Leave it broken? Why would you leave it broken? When you are modernizing in place in enterprise, the very definition of that is that you are like in production. You are serving requests. And so you need to integrate you need to integrate and be able to drop in. And that means even returning errors. So the erroneous behavior, like you see here, which is returning a 404 instead of a 500 error on an illegal input, which is a horrible API, we left it in. We had to leave it in, because it was a drop-in replacement and we needed to be able to do differential testing between the old and the new. So I want to kind of briefly go over a mix-in component pattern that we use. This uses the cake pattern. It's focused around this single trait. This is a trait that supplies the functionality around what's called a URL gatekeeper. So this comprises whitelisting, blacklisting, calls out to Google, safe browsing for just kind of mean people shortening malicious URLs and then kind of posting them to social media and hiding them, right? So we of course did our best to prevent that. But we don't want to be calling Google or calling the other kind of blacklist providers in test. And so we wanted to kind of have a mockable component like this. So here in test, we mocked the URL gatekeeper, the URL gatekeeper component, and then here in our standard issue play framework REST API test, we everything is mocked. You see the top line there, the private API short URL controller. That's the controller under test. Everything else is mocked because it's a unit test for that controller. And then what you're left with is a simple standard issue call to using the standard issue play test constructs. So how do we do the UI? Almost out of time, so I'm kind of going to breeze through this. We trained UI. We got a UI guy. We got a couple of UI people, brought them onto our team, gave them zero training. The funny anecdote here is that they were like, so they're running play with SBT and it's kind of reloading, and they're like, well, I thought this was like a horribly heavyweight framework where it has to, you have to recompile everything and redeploy it and everything. But we're like, no, just do your changes and then kind of reload your web browser. And they're like, whoa, just like PHP or Ruby, and so that kind of blew them away. The new front end looks like this. The front end of Ali isn't the most important. It represents maybe 0 to 1% of the use of the system. The rest, of course, is the APIs. I'm going to skip over this because I'm out of time. But ask me later about patterns for integration semantics using Akka. Who's heard of Gearman? No one? Great. Consider yourselves lucky. So what does 5,000 lines of PHP look like in play? So I'm going to skip over most of this except for this. So here we see the boilerplate that we changed thousands and thousands of lines of PHP boilerplate to. You see our logging constructs, our stats decals to get our monitoring and our statistics around performance. We see the parsing of the parameters, and then here in the for comprehension is just the guts. So that's what the 5,000 lines turns into. Those 6 lines. Yeah, it's all functions and those are calls into components, and of course there's more than 6 lines. But the point is that the point is componentization. So each of those lines represents a component and a step in the system that is comprised together and is individually testable. So why was this a success at the end of the day? Feature flagging and traffic siphoning, because we had a lot of traffic and we could siphon it, we could turn it on and off, and we could turn it on just for ourselves in production, we could turn it off, we could turn it on for only 10% of the traffic. We always iterated into production, clear scoping and estimation of the project, measuring everything, and of course the framework that we all love. So again, we turned this monstrosity into this, saved $30,000 a year right off the top in AWS costs, and untold benefits, monetary benefits around maintenance and all those things that I listed at the beginning. Just kind of worked really, really well. So I want to end with a funny anecdote. So one morning, a friend of mine who works in security at our organization runs up to my desk. And he's like, "Oh my God, the current DDoS in progress against Ali, it just leaped up tenfold. It went from 10 requests a second to 100 requests a second. What just went on? What happened? Did you do anything?" I was like, "Oh yeah, when did this happen? 10 a.m. Oh yeah, that's when we flipped the load balancers completely over to the new system." The new system was able to absorb 100 times more traffic than the old system on 10% of the amount of hardware. The DDoS bots out there on the internet simply went faster because they were single-threaded. We were able to absorb more traffic. So it looked like our DDoS, the current DDoS, was increasing in magnitude. but we were just able to absorb the traffic faster. I think a funny end of that anecdote that isn't true would be like a drop-off of the traffic, meaning that through our sheer ability to absorb traffic, we crashed all those little C programs out on the internet, but that wasn't the case. We just blacklisted the IPs and then it all went away. It wasn't an outage or anything. It was just a it was just a hiccup. Thanks. That's my talk. Time for questions? Questions? Yeah?
So I think you mentioned that this was kind of an incremental or iterative migration. What does that mean? So you got 6,000, you said, PHP files. Were they organized in some kind of way that you could replace it with service calls? Or how did you incrementally move all this PHP code over?
It was around what I called kind of user stories, but what I meant by that was kind of a vertical slice. For the most part, was a single API call. So at the very beginning, it was like the easy ones, like just return a record. There was like a bunch of kind of administrative. There was an administrative backend. So the easiest of the easy, we would modernize and put into production. So that's kind of what I meant by incremental. Like taking a single slice and then going all the way into production, live to live traffic. And then we would kind of feature flag it on, when we were a little bit jumpy at the beginning, we would only feature flag it on during the day. So we would turn it off at night back to the old system. And we had at Hootsuite we have a very kind of I didn't get into this, but a very, very robust feature flagging system. We call it dark launching because it sounds cooler. But we were able to kind of get things into production and very, very safely. Other questions? Yeah.
I got here a little late, but you're using the same data store throughout the migration?
Excellent question. Yes. One of the strategies for this modernization was to use the same data store and wrap a service around it. So we had the service alley data there. That MySQL database on the left there, that was the same one that the PHP was accessing as well. A previous microservices modernization in our monolith, we actually did a partial database extraction, a two-way database extraction using this amazing tool called Tungsten that was able to kind of publish and do like a partial table extraction live. And kind of migrate it forward to another database in both directions that would in turn be wrapped in a microservice itself. But in this case, we were kind of conservative and just wrapped the same database. In the future, the future plans of this, of course, is to write a new service with more robust persistence. And because of the microservices architecture, we'll just be able to swap that in as a service without having to kind of fool around. I mean, migrate the data and then swap it in as a service, implement the same interface.
So when you have a feature both in the old implementation in PHP and in the new one, did you do a test where you split a request to go into both implementations and then check that the reply is the same?
The question was, did we send the same request to both systems and compare the results? Yeah, differential system testing. We did do a little bit of that, but surprisingly, it wasn't as fruitful as you might expect. We did a little bit of automated differential system testing, but it was a little bit too fragile and didn't provide enough focus in our bug testing. So what we preferred was to use the existing production system and our feature flagging to do that. But you're absolutely right. Differential system testing is a super legit way of rolling out an API, a new API in a drop-in replacement.
Yeah, because there was an earlier talk about a tool called Diffie. Did you use that or some other tool?
It wasn't very. It wasn't very. What we tried wasn't very robust. It was. We didn't want to write a lot of code that did testing itself, because of the fact that we had like all this kind of production infrastructure. But we could have easily done that. We didn't perceive the kind of exact results. Even though it was important, we didn't perceive the exact response codes and payloads of our API calls as the crux of the system. The crux of the system was the deployment, the drop-in, the kind of and the re-architecture and stuff. That we didn't want to focus on that when we had running code that calls in already, and kind of we could check the error codes and the kind of the interpretation of that live. But in a system, a drop-in system, where that kind of those contracts were way more important, I think a differential system testing framework would be way more important. Other questions? I think I'm out of time. Thanks a lot, everyone.